Okay, so we've looked at some background, we've looked at an overview. Let's talk about the first premise: the universe had a beginning. We need to define our terms. So if the universe had no beginning, there was no beginning event. That means time never began, it always was. It was eternal. So the word eternal means no beginning. We're going to talk about 4 reasons for rejecting the concept of eternal universe. 4 reasons for accepting that the universe had a beginning. The first one is the Big Bang means the universe began. The second is the universe has not reached a state of maximum entropy. The third is you cannot cross an infinite set of events. And the fourth is you cannot form an infinite set by successive addition. So these first 2 are rooted in science. And when I say science, I mean that there's significant scientific theories that rely on these, and there's been a lot of data collected, a lot of evidence that the theories are correct. The last 2, in some ways, are even stronger than the scientific ones. Although the scientific ones may appeal to us, the last 2 are rooted in logic and math. And so, as we found out in our brief interlude, scientific theories change. So let's just say that the Big Bang theory goes away and the concept of maximum entropy goes away. Well, we're still left with math, the last 2 supporting items. And math is more fundamental than science, and logic is more fundamental than science because science relies on both of them. So the last 2 are stronger arguments, although they're more difficult to comprehend. So that's just a brief introduction. Let's talk about the first one. So what is the Big Bang? Well, the Big Bang, we have to use analogies here because it's hard for us to relate to what actually went on. But the Big Bang, in some sense, is an explosion where there was non-existence, there was nothing. And then suddenly, everything that is came to be and started exploding out. So there was nothing before it, and then suddenly there was everything. There was not only matter, and we can think of that, there was primarily energy, because the Big Bang was such a hot state that you needed things to expand so they could cool and matter could form. So it was largely energy, but it was also length, width, and height. So we think of length, width, and height as a room. Well, what if the room is in outer space? There's no matter there, and there's still these dimensions, and these dimensions didn't exist before the Big Bang. This was pointed to by Einstein's general relativity equations, which is around circa 1917. And I'm going to use some terminology here, which in some sense may be dated, but it's how people talked about it. I'm not sure that everybody talks about it this way, but this is how the analogy went. General relativity theory says the universe began from an explosion that created everything. And if you read some of the old literature, old meaning like 15, 20 years ago, let's say it started from a point of infinite density. And we need to take sort of a sidebar because we need to look at our words because our words can hide meanings. What does a point of infinite density mean? So first of all, the formula for density is equal to mass divided by volume. So how do you get an infinite density? Well, you get an infinite density by there being a volume of 0. So if you have a volume of 0, what does that mean? What is a volume of 0? Well, a volume of 0 is nothingness. It's nothing. A volume of 0 is nothing. Well, let's actually talk about point. What is a point? What is a point that has 0 volume? A point that has 0 volume is a figment of our imagination. It doesn't exist. And the reason I point this out is that when we talk about these concepts, when opponents of the Kalam talk about these concepts, they haven't figured out what these concepts mean in reality. They just use these words. So a point is a mathematical abstraction. It exists in our mind. It doesn't exist in reality. There's no such thing as a point in real life. There is such a thing as a segment, which has a beginning and end, but a point is in some sense 0 dimensions. And something of 0 dimensions is nothing. There's nothing in reality that has 0 dimensions. And so when we talk about these things, you have to get people to define their terms, because what is a volume of 0? It's nothingness. And so in the way that people talked about this, they fooled themselves, because they didn't realize they were actually talking about nothing. It sounds like they're talking about something. So Edwin Hubble first confirmed general relativity in 1927 with the measurement of the redshift. And that was not enough to turn the tide in terms of scientific thought. It wasn't until 1965 with the detection of the cosmic background radiation. And what that is when you have an explosion, you're given off, you hear a sound, but you also see a flash of light. And that flash of light is the creation of electromagnetic radiation. So you could actually have a radio near an explosion and hear static. And the static is because the explosion created electromagnetic radiation the radio hears. Now, in the Big Bang, it's the same sort of thing, in that it created radiation that is sort of permeating the universe. And that's this cosmic background radiation. In 1992, there was an experiment that predicted ripples in the cosmic background radiation. They were discovered with just enough variation for galaxies to form. It was confirmed to 13 digits of precision. And general relativity has many more tests in the last 30 years, more than a dozen independent tests. And the reason I bring that up is to say that it's a pretty solid scientific theory. So I'm going to just go through, not talk about, but just show you several reasons here. These are all from the Reasons to Believe website, and I just copied and pasted them, I'll be honest. So we have 4 on this page. You can stop the video to read them if you want. We have 3 on this page. You can stop the video to read them if you want. We have another 4 on this page. You stop the video to read them if you want. And another 3 on this page. Again, stop the video if you want, or even go to the reasons.org webpage to read them yourself. So there's significant experimental validation to show the Big Bang actually happened. So let's sort of continue talking about the Big Bang. So the universe continued expanding from the explosion. And here's where some of our words get us into trouble again. If you think about an explosion, if you had a stick of dynamite, the explosion radiates outward. And so if length, width, and height were created at the Big Bang, then that has not really stopped. It's continuing to radiate outward. And so the universe is expanding. And it's not, the expansion of the universe is not into a pre-existing space. So if I have a balloon, this is where analogies fail. If I have a balloon and I blow into it, what's happening is the balloon is expanding, but the balloon is expanding into air, into pre-existing air, into pre-existing space. But the universe is expanding, and as it expands, it creates space. So the expansion of the universe is the creation of space and the vacuum in that space. And this expansion is accelerating due to what's called dark energy. So not only is the universe expanding, it's expanding at a faster and faster rate. This was supported by the Hawking-Penrose singularity theorems in 1970. I've actually read these. It's hard to get the paper, but you can. And the important thing here is they took Einstein's general relativity, expanded it, and they created these singularity theorems where they showed time was initiated or created at the creation event. They also showed that under very general conditions, a Big Bang occurred. So you have sort of the experimental data now having a theory behind it, and that was the significance here. In 2003, three cosmologists, Board, Vilenkin, and Guth, published an updated singularity theorem. It's the BBG theorem commonly referred to. And it's a more general statement about the Big Bang. It's larger in scope than the Hawking-Penrose theorem. A point here is it is subject to some of the assumptions of general relativity, although not like the Hawking-Penrose. They say that the only assumption that we made was that the expansion rate of the universe never gets below some non-zero value, no matter how small. The conclusion is that past eternal inflation without a beginning is impossible. So within general relativity, what they showed is there was a beginning event. Now, for those of you who say, well, what about the multiverse? Well, this theorem is general enough that it applies to the multiverse. Now, when I say multiverse, of course, different scientists have different theories of the multiverse. So we can say if the multiverse is expanding on average, which is their assumption, then the multiverse had a beginning. So just saying that there's a multiverse may not help the case of there being no beginning, because it could be the multiverse had a beginning. We'll address the multiverse in a future video. Now, the BBG theorem is subject to general relativity, assumptions of general relativity. So there have been attempts to escape from that theorem by moving beyond general relativity. And I have this table here, which is taken out of the Kalam cosmological argument in the Blackwell Companion to Natural Theology, written by William Lane Craig and Jim Sinclair. And they did a exhaustive 100-page in-depth technical examination of many of these speculative cosmological models that have been proposed. I do want to talk about that word speculative. When you hear scientists or people in the community use the word speculative, what they mean is a story told by a scientist that doesn't have data behind it. So it's a polite way of saying, this is somebody's pet theory that is just beginning to be thought of. And what you could see is, if you read this article, that a lot of these speculative pet theory cosmological models with no data behind them are almost, what do you call it? I would say desperate attempts to escape the notion of a beginning event. Some of them just, when you step back and you read this, you just go, this is so obviously illogical. or this is grasping at straws. I'm just speaking honestly here, reading some of this. So speculative cosmological model is just a story. And they went through this and they looked at it. And some of these cosmological models have an outright beginning event, so they're subject to the singularity theorem. That's the expanding models. The second attempt is to push the creation event to the infinite or near infinite past. So they can say there is a beginning event, but it was so far in the past that it may as well be considered eternal. That's kind of a cop-out, let's be honest. I mean, what we'll see in 1.3 and 1.4 is these scientists should go and look up some philosophical notions about time, because it's not possible to do this. The third is that their models have been shown to not match reality. So what does a scientist do when he's shown his model does not match reality? Well, he's a good scientist. He tries to make his model change. But you can only twist and contort a model so far before you say it doesn't make sense. Or 4, they have extreme fine-tuning in the infinite past. So this is sort of the double whammy, where not only do you have to say there's an infinite past, or the beginning event is far in the infinite past. What does that mean? The beginning event is in the infinite past. How is that different from eternal? But they also add in fine-tuning. So you have a double whammy there. Now, it's not to say that some scientists may come up with some model that breaks free of this, but to be honest with you, these models are becoming so esoteric, it's hard to figure out how they can be validated. So in some sense, we're now in the mathematical realm of imagination. Now, some people may not like me saying that, but I'm just looking at this, having read a bunch of the material and having looked at how people go about this. When we talk about the multiverse, we'll see that, and maybe my thinking is colored by how people talk about the multiverse. It's another video. So if we look at the Big Bang, if you reject the Big Bang because you don't like the universe had a beginning, that means you're rejecting a very well proven theory of science. There are consequences. So the consequence is, if you throw out this scientific theory, which has significant supporting evidence, why don't you throw out any other theories? Or why accept anything from science? So if you're going to ignore this, then you need to come up with an alternative, and you need to provide the basis for rejecting it. Otherwise, you're being arbitrary. Perhaps you're being narrow-minded. So let's talk about 1.2, and the universe is not at maximum entropy. So I'm going to use a very high-level concept here, and that the universe is like a battery. If you think of the sun is generating energy just like a battery, and eventually we know that the sun is going to run out of energy. The sun is going to stop generating light. It's going to fold back on itself, and it'll probably go nova. But if you take all of the stars in the entirety of the universe, right now they're all generating energy, and at some point they're all going to stop. Just like a battery wears down, all of the stars are going to wear down. All of the ways of generating energy are going to wear down. And so entropy as a concept is that, applied to the entire universe, is that the useful energy wears down over time. This is the second law of thermodynamics. And a generic way of thinking about this is the loss of ability to do useful work is called entropy. And so the second law of thermodynamics says the amount of energy to do work is always running out over time. And you think about warm cup of coffee in a room. Well, the warm cup of coffee, the heat from the coffee warms the room, and the coffee grows cold, and the coffee reaches the same temperature as the room around it. So it reaches an equilibrium. And because there's an equilibrium, that means you can't do work. Because work, well, you can't do work because you can't find a difference between things to cause work to happen. For example, a battery has a difference. It has a voltage across a positive and negative terminal. A dam, you can do work because you have the pressure from the water. But if all the water is at the same level, you have no pressure. So it's the same sort of concept. Now notice that this never works in reverse. You never have a warm room heating a cup of coffee. You never have your bathroom warming your bathtub. So this is a one-directional process, and science depends on this not happening in reverse. It depends on it being a one-directional process. In fact, I was perplexed by some scientific papers, and I queried Jim Sinclair on this, and the concepts that they were talking about were time. And what he said to me is, well, physicists think of time in terms of the second law of thermodynamics, how systems run down. And that's where I was getting confused, because I was thinking of time as seconds, or time as a measure of passage. And he clued me in and said, no, you have to read this as time is in terms of thermodynamics. And so in some ways, the notion of time is, or the notion of thermodynamics is so embedded into this. It's embedded in the notion of time from science. So the point here is the universe is running down irreversibly. If we want to formulate this as an argument, it would be a proof by contradiction. If the universe always existed, it would have already worn out. We would have reached a state of maximum entropy. They call it heat death. Maximum entropy is where everything is spread out. It's an equal energy level. However, a state of maximum entropy has not been reached. So the universe began to exist. Therefore, the universe had a beginning. So this is, I'm laying this out so that as an argument, if you don't agree with it, you need to figure out which of these premises is false. Let's look at what some of the scientists say. Today, few cosmologists doubt that the universe, at least as we know it, did have an origin in a finite moment in the past. The alternative, that the universe has always existed in one form or another, runs into a rather basic paradox. The sun and stars cannot keep burning forever. Sooner or later, they will run out of fuel and die. Well, let's look at some words. If the universe has always existed, there's a basic paradox in that they will run out of fuel and die. The same is true of all irreversible physical processes. The stock of energy available in the universe to drive them is finite and cannot last for eternity. This is an example of so-called second law of thermodynamics, which apply to the entire cosmos. Again, it's applied to the whole universe. Predicts that it is stuck on a one-way slide of degeneration and decay towards a final state of maximum entropy or disorder. As this final state has not yet been reached, it follows that the universe cannot have existed for an infinite time. So the stock of energy is finite. We're looking at the entire cosmos. The final state has not been reached. Therefore, the universe has not existed for an infinite time. Paul Davies is a physicist. This is an even more critical statement to those who would say that thermodynamics doesn't work. And I have had actually an engineer tell me he didn't believe in thermodynamics, which was kind of interesting, because his whole sort of discipline depends on thermodynamics. If someone points out to you that your pet theory of the universe is in disagreement with the Maxwell's equations, then so much the worse for Maxwell's equations. If it is found to be contradicted by observation, well, these experimentalists do bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for the theory to do but to collapse in deepest humiliation. This is how deeply ingrained the second law of thermodynamics is. And this was said by Sir Arthur Eddington in 1948. So, rejecting the universe is not at maximum entropy, meaning the universe had a beginning, is again rejecting one of the most proven foundational laws of science. And if you're going to reject it, I would say this is an ad hoc decision that needs significant justification, or it's an act of prejudice and bias. Science requires the law of thermodynamics. If you do not accept this proposition, then you are rejecting science. Right? So what's the consequence of that? Will you live your life as if you reject science, or do you live your life as if science is real? Because if you live your life as if science works, then you should accept the universe had a beginning. That's the consequence of rejecting this supporting factor. So, just as a quick recap where we are, if the universe had no beginning, it was eternal. And we're given 4 reasons for rejecting an eternal universe. The first one is the Big Bang means the universe had a beginning. The second is the universe has not reached maximum entropy. The next 2 we'll look at, you cannot cross an infinite set of events, and the fourth is you cannot form an infinite set by successive addition. So we've looked at the scientific view. The next step is to look at the logical view.